Dear students, welcome back. In the previous lectures, we had given the definition of an ordinary differential equation, linearity, its existence results, uniqueness results. We also talked about Picard's iterative process and so on. In this week lecture, we are going to see the special forms of first order differential equations for which one can obtain closed form solutions. So we'll start with and I've already mentioned in the earlier lecture that we are going to do 6 types of first order differential equations for which one can obtain closed form solutions. So today we will do 2 types of out of the 6 types, which is the separable type and the homogeneous type. Okay, so let's start with the separable type. So what is a separable ODE? So recall that our ODE is of this form, that is y prime is fxy. Okay, our ODE is this form. So we say a first order ODE is of separable type is of separable type if fxy is of the form mx over ny. So basically what we are saying, separable type basically means that this fx is actually of the form minus m, a function of x only, where and the denominator is a function of y only. Why? If this is possible, then when you write it in a differential form, you have this form, where with the x differential you have only a function of x, with y differential you have only a function of y. So when we say separable, we basically mean this, that the variables are separated here. Okay, and this makes it easy to integrate the differential form to obtain a family of solutions in basically a solution in x and y variable, right? So this is what we mean when we say a first order ODE is of separable type. Okay, so basically the given coefficients have this form that you can accumulate all the y coefficients with the dy differential and all the x coefficients with the dx differential. So the advantage of the separable type is that once you have the separable type like here, and to find the solution of a separable ordinary differential equation, you just have to integrate with respect to the x variable and integrate with respect to the y variable. So here you integrate with respect to the x variable and with respect to the y variable. 0 on integration is going to give you constant. So you actually have a solution f x comma y, a family of solution f x comma y equal to c, where f x y is precisely this, after whatever you get after you integrate. Okay, so that's so this is the most simplest ODE that you can solve. Okay, this is which is right, and this is due to the fact that you could separate the variables. So let's look at a quick example. In fact, we'll see more examples as we do more problems. I'm just going to do one example just to get across the idea. So take this ODE, which is in the separable form, because with the dx with the x differential you have only a function of x variable, and with y you have the function of only y variable. This is some we have already seen in the previous lecture. We have already solved separable equation without actually mentioning separable ODEs, right? So what is the idea here? You just integrate with respect to the x variable here, integrate with respect to the y variable here. On integration you get minus 1 over x, 2 over x square, and from here and from here and from here you are going to get 1 over y minus 1 over y cube, and this is going to give you c. Okay, so this is your family of solution, and we have already said that if it's a first order ODE, then you have one parameter family of solution, and here that one parameter is c. So for a separable ODE it's simple, you just have to integrate and you have a family of solutions. Okay, now next go to the second type of ODE, which is called the homogeneous ODE. So before that, let's see what is homogeneous. So we say a function v, okay, we say a function v which is an R2 function, right, which is a with the domain, so it's actually a two variable function. We say any function, so any two variable function is homogeneous of degree n if vtx ty is t power n vxy. So the degree n is this n that appears in the power here. So if you multiply any scalar t in both the variables x and y variable, it comes out with some power, whatever that power is the degree. So homogeneous of degree n means vtx comma ty. So wherever you have x and y variable, replace x with tx, y with ty. You can then observe that, and if that t comes out like t power n, then that function v is said to be homogeneous of degree n. So let's see an example to get across the idea. For instance, take v to be x square plus y square. This is homogeneous of degree 2. Why? If you take v tx ty is equal to, so wherever you have x, you put tx, wherever you have y, you put ty, right? So this is tx whole square ty whole square, and you see this is tx square x square, t square x square, t square y square. So it's t square x square plus y square, but x square plus y square is precisely v, so it's vxy. So this function v is homogeneous of degree 2. This is an example of a homogeneous function. So whenever a function v has this property, you say it's a homogeneous function of degree 2. So now what is a homogeneous PDE? No, sorry, homogeneous ODE. Okay, so what is a homogeneous ODE? So we say an ODE of this form is homogeneous if this f satisfies this property. Basically what we mean is that when I say, so in 3.3 is a differential form. Okay, so what is the differential form? In 3.3 you have mxy dx plus nxy dy equal to 0, right? That is what the difference. So we have already said that any ODE of this form can be equivalently written in this form. Okay, they can be interchangeably written like this. So what do you mean by homogeneous ODE is this m and n that is appearing, this m and n that is appearing here, they both are homogeneous of same degree. So both m and n should be homogeneous, and both should be homogeneous of same degree. Now this, if we rewrite in this form, what do we get? It's y prime is equal to minus m xy n xy, right? Now if both m and n are homogeneous of same degree, then this basically means, right, this is your f of xy. So now if you look at f dx dy, wherever you have x and y, you put dx dy, so this becomes dx dy, dx, this here it becomes dx dy, dy, dx dy. Now by the homogeneity of m and n, right, they are of same degree, so you will have some t power, let me, okay, right, so let me write on the top. So so let's start with f of dx dy. This is m dx dy by n dx dy. Now both m and n are homogeneous of same degree. So let's say the degree is n. So this becomes, sorry, with the minus sign, m x comma y by t power n x comma y. But since there's a t power n and t power n both are denominator, what you are left is minus m over n, which is precisely fxy, which is this condition what we have here, right? So what we are saying here is that an ODE is homogeneous if in the differential form m and n are homogeneous of same degree. Equivalently, in this form, it's homogeneous if f is homogeneous of 0 degree. Okay, as an example, you can look at this form, which is this ODE in the differential form. This is homogeneous. Why is it homogeneous? You can verify that wherever you have x and y, if you plug in dx dy, here you are going to get dx. So this is whatever you have here is homogeneous of degree 1, that n here. So in this case n is x, right? N is x, which is homogeneous of degree 1. What about here? This is again dy plus root t square x square plus y square. This t square will come out as t and that t. So this is again a homogeneous of degree 1. Okay, so this is homogeneous of degree. This is so this ODE is homogeneous because the m and n coefficients in the differential form are homogeneous of degree 1. Okay, so why are we looking at this type of ODE which is homogeneous? Because we will now, so we are now going to see a result or a theorem which is going to tell you that homogeneous ODEs can be very easily transformed, okay, into separated variables. Basically, homogeneous ODE can be transformed to a separable ODE. Separable ODE. Okay, so and we have already seen how to solve a separable ODE, which means any homogeneous ODE can be transformed to a separable ODE. Since we can solve any separable ODE, we can actually solve any homogeneous ODE. Let's look at the theorem. So what is the theorem saying? If you have an ODE which is homogeneous, then if you employ this change of variable, that is y, introduce this new variable z, which is y over x, Okay, if you introduce this new variable z, and if you rewrite the original ODE in z and x variable, then you are going to get a separable ODE in x and z variables. Okay, that's the theorem. So let's try proving it. So start with the homogeneous. So what is given to us is that this ODE is homogeneous. What does homogeneous means? Homogeneous means that f dx, so this f is homogeneous of degree 0, right? In this form, f is homogeneous of degree 0. So f dx dy is f of xy for any t, for any choice of t. So now, ideally, when you verify this thing, you fix a t and then you verify this, right? So for any t, this is valid. So now what we do, we are going to choose a particular t which is 1 over x. So since this is valid for any t, this is valid for any 1 over so for any 1 over x. I mean, so this is valid for 1 over x for any x. So instead of t, I use t equal to 1 over x. So what I get is f1 comma y over x is f of xy. This property is a particular case of the previous property. So the fact that the ODE is homogeneous gives me this information, right? So this gives us this fact. So homogeneous implies this, that f1 comma y over x is f of xy. Now what you have here is f of xy, which means the ODE which is given to you can now be equivalently written as f1 comma y over x, right? Because f of xy can now be replaced with f1 over x. So do that substitution here. So the ODE becomes y prime of 1 comma y over x. Right? So the ODE becomes this. Now you introduce this change of variable that we said, which is z equal to y over x. Introduce this new variable z. Okay, so introduce this variable z y over x, which means y is x z. If you use this information in this ODE, you get y prime is this and f1 comma y over x is this. So the ODE becomes now an ODE in z variable and x variable. Okay. Now this ODE, if you observe, is in the separable form, because this ODE can be equivalently written, this ODE now can be equivalently written in this form, and this is in the separable form, right? The numerator is z dependent, the denominator is x dependent. So you can actually have, right, you can bring all the z variable on, say, left hand side, all the x variable on the right hand side in the differential form. Okay, so we have converted the given homogeneous ODE into a separable form ODE. The only catch here is that since we use the substitution that z equal to y over x and x is in the denominator, we have to ensure that whenever we do this transformation, this change of variable, right, this change of variable, we are outside the region which does not contain x. So we have to exclude the region where x is 0. Right? We can't divide by 0. So this transformation is possible as long as you are outside the, as long as you are in a interval which does not contain 0. Okay. So this theorem proves that any homogeneous can be reduced or transformed to a separable ODE. Since you know how to solve a separable ODE, you know how to solve a homogeneous ODE. Let's look at some examples. Okay, here I'm just going to derive the solution in the more general form. So you are given a homogeneous ODE. Okay, now by the previous theorem one could transform it into a separable equation in the z and x variable. Okay, now in the separable form you can solve it. You just integrate it in the z variable and x variable. This is your fx comma y equal to c. So you have one parameter family of solutions. Now since your original equation was an x and y variable, you would like to compute your solution in x and y variable. So rewrite in the x and y variable form. So this is your solution where your capital, so this is your capital F. So fz is this, that's what I've said here. Fz is that first integral. Okay, and you replace z equal to y by x, then you have the solution in terms of y and x variable. So you have a formula for finding the solution in the x and y variable. So any homogeneous ODE can be solved using just the technique of separable variable. So let's look at some examples. So consider this ODE. This is in the differential form and this is in the non-linear form. I mean linear in the highest order. Okay, so is this homogeneous? Let's verify. So what you have to check, this term and this term should be homogeneous of same degree. You see wherever, so in the first term here you have t square x square minus 3t square y square. So it is homogeneous of degree 2. Here again 2 tx ty. This is again unable to write. This is again homogeneous of degree 2 because there is a t here, so you have t square. Okay, so you have a t, so this is homogeneous degree 2, so this is a homogeneous ODE, there is no confusion about it. Now how do we solve it? You do the, so this whatever I just showed you is what I have written here. So m is homogeneous of degree 2, which is, this is m and this is n. N is homogeneous also of degree 2. Okay, so it's a homogeneous ODE. So the given ODE is homogeneous. Now you use the substitution y equal to zx. So this y prime becomes this, and whatever you have here becomes this, right? Y by x square. So this again rewrite, bringing this z as minus z here, you get xz square equal to z square minus 1 over 2z. This equal. So now you have a ODE in z and x variable and it's in the separable form. You see this side there is no dependence on x. So you can take it to this side with z and this x can come the other side. Okay, so this is a separable type ODE with dependence on z variable here and x variable here. So now how do you solve it? You integrate it with respect to a z variable and x variable. So if you integrate it, you already see, so if you integrate this, this is log of z square minus 1, this is log of x. So this is log of z square minus 1 minus log of x, some constant. For convenience we are writing that constant as log of mod c. So this is equivalently z square minus 1 equal to cx. So this is your one parameter family of solution in z and x variable, you can rewrite it in terms of x. So replace this fact that z is y over x. So you get y square minus x square. So this is the family of solution in the one parameter family of solution in the x and y variable. Okay. So let's do another example. In this time we will take a initial value problem. That is, you have the ODE and you also have a initial value prescribed. Okay. So more or less in this entire course, whenever we do an example, I'll try to do one initial value problem as well wherever possible. Okay. So just another example. So first of all, whether so is a given ODE homogeneous, or is it separable? It's not. It's not separable because it's not obvious here because this depends on both x and y variable. So next is type that you have known is homogeneous ODE. Is this homogeneous? We have already seen it when we gave the definition of homogeneous. This is the example that we verified to be homogeneous, right? So it's the same ODE I have taken for convenience. So this one, we have already verified that it is homogeneous. Okay, that's the ODE that we have taken there. Okay, so this ODE is homogeneous. You can verify. Okay, if you have not understood what how to verify, please do it now because this is a good time to do it. We have already verified this. So this is an homogeneous ODE. So how do we solve it? Just use this change of variables. So we rewrite this in this form. Okay. Now you use the change of maybe use the change of variable y equal to zx, so that OD will become this. So if you notice, you have y prime will become whatever we have here by the change of variable, and whatever you have here, this y by x will become z, and this will become 1 plus z squared. Okay, so what you do that computation, you will see that. So you have now a separable ODE. Now you have z here, you have z here, that will cancel out. So you actually have equivalently this ODE. So there is a z dependence here, there is only x dependence here. You can separate the x and z variable. So now you have an ODE in a separable form. Now how do you solve a separable ODE? So how do you solve a separable ODE? You just integrate it. So if you integrate it, you are going to get log z plus root z square plus 1 minus log x equal to log mod c. Okay. Now equivalently, this can be written as z plus root z square plus 1 equal to cx. So this is the one parameter family of solution that we have obtained. Now this is an initial value problem. So we have now that we have a general solution. So this is a general solution, right? We have a family of solutions now. Now for initial value problem, you can use the initial condition to pick probably one solution, right? So the initial, what is the initial condition given to us? Yeah, the initial condition given to us is that the value of y is 0 at x equal to 1. At x equal to 1, y is 0. So let's use this information at x equal to 1. Okay, so we have the solution in the x and y variable. So now you have plugged in back z equal to y over x. So you have solved you have the one parameter family of solution for the given homogeneous ODE. Now we need to use this initial condition. So you put x equal to 1 and y equal to 0. So 0, 0, 1, 1. What does that give you? That gives you that mod c is 1. So that gives you mod c is 1. So use that information here. The mod c is 1. You have, this is the particular solution, right, for the given initial value problem. So you have solved the initial value problem. in x and y variable. Okay, so this is where we will stop. I made this short lecture because see, I am more or less I am planning to um, kind of give the contents together. So some lectures will be of shorter duration, some lectures will be of longer duration, but the total time taken for the entire lecture is the usual time taken to finish the course. So don't worry about it. So here, because I don't want to split the topics across lectures, because now we are doing it via video lectures, and so you may lose the continuity. So I will stop here with homogeneous ODE. So we have done two types today. In the next lecture, we will do the third type, which is the exact equations. I'm sorry, exact ODE. Okay, this is something which we will do in the next lecture. So see you in the next lecture. Thanks a lot.